The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, welcome to the midweek cruise with SkyTour Radio with me, Mark D'Antonio. That's me right there. So, and then look at that. That's Tara. Hi, Tara.
Hi, how are you?
Good. How are you, hon? It's so nice to see you.
Nice to see you. Glad to be here. Hello, everyone. Hi.
Okay, well, we'll see you.
Oh, no, I'm not ready to go.
Oh, neither am I. So, SkyTour Radio, we're going to have fun tonight. We're going to talk about the sun. Now, why would we talk about the sun? Well, because it's the bright object in the sky during the day that everybody sees, and many of them just say it's a hot ball of gas. Well, there's a lot more to that hot ball of gas than you realize, and we're going to cover some of that tonight. It's pretty cool because understanding the sun is the first thing we did as astronomers to try and understand the rest of those dots in the sky. Once we realized, and I know this sounds crazy, once we realized that the rest of the dots in the sky were also other suns, quote unquote. And then, and only then, did we discover that there are other suns out there that are so much more massive, so much larger than our sun, and on the flip side, so much smaller in some cases. Literally only a little bigger than the planet Jupiter. So it's pretty cool stuff, you know?
Yeah. Well, Jupiter's still pretty big.
Yeah, it is. It's the biggest planet in the solar system, right?
Yeah.
Yeah, 87,000 miles diameter, roughly. I mean, we're talking a gigantic ball, you know. I mean, you could fit 12 Earths across the face of Jupiter, so it's you know, pretty big, you know.
And so a sun that big probably is more dense, maybe, or maybe not. I don't know.
Good point. No, good point. Yeah, the problem with Jupiter not being a star is that it's not massive enough. So how do you make it more massive? You add mass to it, which would increase, as you just pointed out, its density.
Right.
And if you can increase the density enough of Jupiter, you could, quote unquote, turn it into a star. Because all it matters is that the mass is bearing down with its weight at Jupiter on all sides of the planet on that core. And in that little core inside, in here, that little core, about 15 or 20% the size of the stars that we typically see, is the hottest point. And that is where you can then take the hydrogen, which is what Jupiter is made of mostly, and stars are, and start a process called nuclear fusion. Fusion is the power of our sun. It's the power of most normal stars, as we'll see. You know, and it's a very complex reaction if you let it be. If we're going to not talk about it with the complexity.
If you let it be, that's funny, as if we have control over how the sun works. Or maybe that's not what you were saying. I don't know.
It sort of is. If you allow certain things to go assumed and not actually try to think too deeply as we're moving forward, then you'll be able to get the big picture. And then once you have the big picture, you can drill in on all the little tiny spots that need filling. And let me tell you, there's millions of them when it comes to fusion and the way stars work. There's so many different types of stars. It's incredible.
It's neat. Yeah.
And guess where else we see the stars a lot?
In Hollywood?
No. Where do we see the stars?
Well, in galaxies, you mean? Or during the nighttime?
Oh, yes. That sounds like
you're talking maybe during the eclipses.
Not well. Okay, yes, during eclipses, which we're going to talk about tonight.
Help me.
During SkyTour live stream.
Oh, duh. That's like a given, like an understood, but I apologize.
Right.
Yes.
It's a given for you and I, but not for everybody, right? I mean,
SkyTour live stream, that's almost the only place you can go to see it live. So
I know. We take great photos. We we take these pictures like that when you just saw, galaxies, that one there.
Oh,
And
we're
those are.
blocked. Let's go another.
Oh yeah, they're in the background. I'll get them
Yeah,
forward. Don't
that's
worry.
good. Okay.
Yeah, but the whole point is, we created a couple of really nice observatories. One out in well,
Oh,
Wickenburg.
there you go.
Look at that guy with those white legs. Oh my gosh, that's so embarrassing. That's so
Ah,
embarrassing. What's not
that's
embarrassing is the STLS on that door. That was all you. That was all
ah,
her.
thank you.
All Tara. She created those out of colored bottle caps, and she
Yeah,
didn't paint them. That's the natural color. And she created the Orion Nebula, which is really, really pretty.
yeah.
Now it's really pretty out there. I mean, this is the kind of sunsets we see out there. This view you see right here,
Mm.
it's the orange on the horizon. That's the remnants of the sunset. And still, we can see all this Milky Way. I took this photo with a camera on a tripod. Look at that.
And sun's not even completely down yet, and there you
Yes,
go.
and the Milky Way
Mhm.
goes right through the sunset. I mean, that's how beautiful it is out there. And that's a
Gorgeous.
gorgeous
Mhm.
location, yeah. And when it's cloudy, you still get some pretty skies like this, right?
Yes.
Yeah. And when it's not, well, you get the buildup of the anticipation. Oh wow, there's the waxing
Mhm.
crescent moon. Okay.
Beautiful.
And we have this beautiful beautiful sky coming. Anyway, so we did put in the telescope out in Wickenburg, and then we ended up putting a second one in an existing facility out in Benson, Arizona. And the one out in Benson is pretty interesting because it's a beautiful location. There's an observatory up there. Okay.
So cool. The
Yeah,
big one.
that's the big observatory on the hill right near
Mm.
us. And then down below, just on the lower ridge here, you have this line of box looking objects. Each one of these boxes has a professional astronomer in it.
That is so neat. Poor guys. When are they going to let him out?
I know. Okay. Well,
Mhm.
nearly all of them operate remotely like we do.
Amazing.
Okay,
Amazing.
this is our building here, and
Mhm.
this is right after putting that white door on. That we had to change the door so that we could open the door outward, which makes more room on the inside.
Hello. Yeah.
The other one's open inward, which is like, okay, that's weird. So the ladders were used to get up high to do stuff, and then inside we added this large telescope inside.
Oh,
You can see it up
beautiful.
towering over my head there. Either I'm 3'5" or that's a big telescope. I think just a big telescope. Yeah. So
Tall.
we ended up creating this to do a lot of stuff for us. And one of the things that this telescope can show us is gorgeous views of close up objects. The Sonoran telescope out in Wickenburg area, that telescope is a wide field system. So when we use that one to look at objects in the wide field, I mean, we'll see these incredible vistas that are just stunning, and we'll see like whole objects. Plus, well, I'll give you an example. This is an example. This
Ooh.
was taken with our wide field system. That's a supernova remnant, and that's literally about a third of it. And that's the side toward the west. And then there's a whole side toward the east, which is on the other end. And I don't have that picture. But this telescope is a lot different. It actually has what's called a higher focal length, the one in Benson, and it
Mhm.
allows us to see things that are much more close up. And on the back side of the telescope, which is to the lower right there of the tube, you see that red barrel looking thing. That
Yes.
red barrel is actually the camera, and just to the left of it, that's a filter wheel. So I have different filters in there that we can circle around dynamically and remotely, and I change them all the time and take pictures with them. And so when we take photos there, then it kind of looks like this to the audience.
Mhm.
Okay, these are two galaxies that you see on the left side. On the right is the guiding system that's superimposed over the application, and this is what people see. Me, and what's missing is me in the lower left corner as a little tiny image because I talk to people and use my hands a lot, and then
Little
I'll go up
talking
into the
head.
view. Yeah, I'll go up into the view and point things out and stuff, right?
It's really fun that you can do that.
Yeah. So SkyTour live stream. I mean, I think we've been going since 2016 with that. I think. right?
Boy, time flies when you're having
Yeah,
fun,
yeah.
working
I used,
hard.
I used to have a dome on my front lawn, and I'd go out there all times of the year, and whether it was winter or not, it'd be 20 degrees, 10 degrees, 5 below. I'd be out there all bundled up, talking to people around the world, broadcasting what I'm seeing. And I would actually run the telescope from the computer out there. And I thought, well, if I can run it from a computer out there, why can't I run it from one of my computers in here? Well, you know what? I'm a genius. It took me about a year to figure out that that's what I wanted to do. A year and a little bit of almost frostbite on my right hand here. Okay.
Yes.
Then my mouse finger actually almost got frostbit.
Oh,
Because that was the only exposed part. So it was pretty cool. And then I ended up getting rid of the observatory because I outgrew it. And the telescope that was in the observatory is right there. You can see it right
yeah,
there
in the corner, in that dark
in the
little
corner.
corner.
Yeah.
Yeah.
And that telescope was served well and served us well for a SkyTour. And it just became time to get something different. So we ended up getting a beautiful new system to put out in the observatory, and in the Sonoran Desert, the Wickenburg one.
Right.
Yeah, and then we ended up getting a second telescope, which you saw in this picture here. This is Benson.
Mm-hmm.
That's an 11-inch Celestron telescope, and that one's an inch larger than the 10-inch one we have out in the Sonoran. So we have SkyTour 1 and SkyTour 2. This is SkyTour 2. And so it gives us these tremendous views. The capabilities are just incredible. And it blows my mind every time.
Well, you think
You
it
know?
blows your mind. What do you think it does to us? We don't ever get to see things like that often.
Well, I guess that's true.
Where
That's true.
it's amazing every time. Even the things that you photographed and we see again are just like breathtaking.
Yeah.
So,
Hey, let's say hi to Michael Bolton. Hi, Mike.
hey, hi, Michael.
Thanks for joining us from Australia. That makes oh gosh, he's like let's see, we have
early morning maybe. Oh.
we have several we have several other people. They're about 12 hours different from us. So it's probably around noontime for him, maybe a little
Okay.
further. Maybe mid-morning. I'm not sure. He'll tell us. Well, anyway, nice to see you, Michael. Thanks for joining us. And one of the things I'll mention, since that comment from Michael is from the Southern Hemisphere, is that we are looking into the potential for getting a telescope down in Australia somewhere. Now,
Ooh.
that's not even yet in the plans. Yeah, we are. This is my design. It's me talking.
Ooh.
I've never seen the Southern Hemisphere sky. I'd very much like to see the Southern Hemisphere sky.
Most of us haven't seen it
Yeah.
either, Mark.
That's true. That's
We
true.
support you in that. We support you in
Yeah.
that endeavor.
Yeah.
We'll see.
Well, you got to support me. You're part of SkyTour Live Stream.
It's easy to support you. It's just natural. So
Yeah. Well, and you make it a lot of fun too. So you and Marianne both make it a lot of fun. So that said, we were going to talk about the sun tonight, but one thing I wanted to mention before we get going is that down in the Southern Hemisphere is a sibling of ours. A sibling.
Okay.
Now, when I say sibling, I mean a twin. I mean an exact twin. And what does that mean? It means that, as we know, stars form in clusters. We watch stars form in these clusters, and when they form in clusters, they end up being, very, very, very much the same composition. A lot of the times, the mass might vary a little bit. Okay, but when they form there, they tend to form in groups that are all the same composition, formed from the same stuff that was in the original cloud from which the star formed.
Okay.
And so we see that in clusters all over the place. And so therefore, it was natural that sooner or later we'd say, where were we born? And do we have any siblings of our own? Because we're a solitary star. But it doesn't mean we were born alone. It means that more than likely we were in a cluster that since going around the galaxy as we have almost 20 times since our inception 4.5 billion years ago.
Wow.
4.6 billion years ago. Was it 230 million years every time it goes around? But it goes so, it's getting
Cool.
tugged and pulled. And if we're in a loose collection of stars, they're all going to get pulled away and moved. And
Yeah.
so the hunt was on to find a star that looks just like the Earth. Okay. And it's just like our sun. And that particular star was missing. We couldn't find it, and I'm sure there's more than one star, and it looks like Tara has left us for the moment, but I assume she'll be back. So when you talk about a sibling for us, we actually found one, finally, one so far, and it's in the southern hemisphere, and that's kind of cool, being in the southern hemisphere. So that said, I'm pretty sure that we will. I'm pretty sure that we will find ourselves more of them, and it's not just a long lost twin, as Daisy and Zoe Amethyst say. Daisy and Zoe, by the way, are phenomenal listeners to SkyTour and viewers of SkyTour live stream. So it is a long lost twin in a sense, guys, but we're also going to find more of them. Most likely, because we didn't just form with one other star. We certainly formed with many other stars in all likelihood. So we're going to try and find those as well. So that said, I'm going to show you, we're going to bring up this talk. This is a talk, it's called Solar Eclipses, but we're going to be talking about the sun a lot as well. Okay. And we can hope that Tara makes her way back in. So that said, we talk about solar eclipses and things. Oh, we got, now see, here's somebody else. Okay. And there she is. Hello again. Welcome back.
Hey, sorry about that.
Yeah, that's okay. I was wondering if maybe, your house was power went out or something,
Well, I heard about the sun and how hot it was, and I got kind of afraid, so
Oh, you went and hid for a while?
I had to just meditate for a moment, and now
You
I'm
had to
back.
move the
I'm so
cats into
great.
their
And herd some cats.
safety enclosures.
Herd some kittens.
Right, because herding cats is so easy.
It was actually my fault.
What are you doing in my radio show?
Oh, hi, Bill.
And so Bill caused it, huh?
Bill caused it, but Bill got me back in here, so that's all good. It's all good.
Where do you think you're going, Bill? Get back here.
I caused him to leave that time.
Oh, did you?
No. Just kidding.
Yeah.
Mm-hmm.
All right, Bill, come on, get back here. All right, now explain. You're muted.
I'm not going to explain technical issues that just happened during the I'm more interested in seeing what solar eclipses are all about.
That's all that matters. That's right.
Exactly. And matter of fact, before I leave, when is the next partial or full solar eclipse?
Good question.
I'd have to look that up. I don't know. Because they're very rare to pass over us. Although tonight I'm going to use the example of the one that passed through the United States just most recently.
Oh, cool.
And I saw it. It was beautiful. Interesting thing about solar eclipses, you'll notice when I talk about it, the moon blocks the sun, of course, because it's on the other side of the earth toward the sun. And we'll talk about some of the interesting facts about solar eclipses that you may not know. Anyway.
Cool.
Right. And now I'm going to remove you, Bill.
Bye.
I have such power.
What goes around comes around,
I know, right? So, in terms of solar eclipses, one of the things I want to mention is I talked about the different kinds of stars when we looked at our sun originally. We noticed a lot about the sun. And once the prism was invented, okay, we noticed that there was a rainbow. So you saw light that was red, orange, yellow, green, blue, and violet. Okay. Blue, indigo, and violet. Okay, that's an in-between color there.
Okay.
And that's Roy G. Biv. Actually, Roy, red, orange, yellow, and then G for green, and then blue, indigo, and violet. So Biv. And when you're in grammar school, if you had a good science class, like I did,
I didn't.
You would know Roy G. Biv before you got to 5th grade. Okay. Then again, I had typing in 2nd grade, and I could do 60
Wow.
words a minute by junior high school, 7th grade.
That's impressive.
I could type as fast as I could talk.
That was
And
before really electric typewriters too.
it was, that's correct. And
Mhm.
so we had to just go tick, 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 and
It's
I
fun.
learned how to do that. And as a child, that was a very successful program. And I know I'm diverging from our topic a little bit, but it actually goes to show you how capable humans are and how they've evolved here with
Mm.
skills that, when taught at the right age, can persist for a lifetime. And that's an example of one of them is that very thing is typing, as simple as that is. There's still people that
Mhm.
say, I hunt and
Yep.
peck. Okay. All right,
Yeah.
fine. But knowing where all the letters are without looking at the keyboard was the biggest thing. And of course, I had a teacher in the typing class that
As he
if I was
grimaces.
caught looking as I did, yeah, because if I was caught looking at the keyboard, she'd come over and slap my hand.
Ah,
Yep.
ruh-roh. We used to get paper taped over the top of our hands, taped to the typewriter so you couldn't see your hands. So.
Oh, why did they think of that? I know,
Mhm.
because the teacher wanted to beat us.
Yes.
Wait a minute. Come to think of
Is
it,
it-
I'm the only one she ever hit. I was kind of a disruptive child, actually.
Well, you're probably very inquisitive and had a lot of questions.
I
and
think a
stuff.
lot of people
Mhm.
know that I was just a disruptive child. So, uh, so when we started looking at the sun, we learned about the spectrum, the colors, Roy G. Biv, and then we noticed that sometimes when you looked at the sun a certain way with a certain instrument, you'd see that there were these vertical dark lines in the sun's spectrum. And this was interesting because these vertical dark lines, you understand what's called the continuum, the red, orange, yellow, green, blue, indigo, violet,
Yeah,
and it's the rainbow. It's what
pretty.
water droplets do that a prism does. And in fact, seeing a rainbow and deducing that it was water droplets is something that can kind of lead anyone who's looking at that to say, that's got to be water droplets up in the sky because it's just finished raining, and then over there it's raining, the sun's behind me. That's got to be water drops doing something to the rain or doing something to the light. So you could see how you might make a water drop and shine a light at it and see if you can see some kind of rainbow.
Mhm.
And sure enough, you can if you do it the right way. So that's the voyage of discovery that somebody somewhere took and ended up going down, well, the full path with it and figuring out that this full spectrum of the sun's light, we'll call that the continuum. However, if you do a slightly different thing, if you only take a tiny narrow slot of the sun's light, just a slit, like a slit, just like this. See my eye through there?
Yeah,
My eye,
vertical
yeah.
slice,
A
right?
vertical slit, a little tiny slit, a
Mhm.
little tiny opening, and you pass that same light through it. Well, then you can see those vertical lines in the spectrum. And if you focus on that slit with your camera, okay, or your eye, if you're projecting it, then you will see that you will get just these vertical lines. And those vertical lines were a mystery until they realized that these vertical lines were caused by chemicals,
Oh,
elements in the atmosphere of the star. Now, wait a minute. What means, Mark, stars have atmospheres? No, they have a core and they have an outer envelope, but we call that the stellar atmosphere.
right.
Okay. In fact, there's a famous book by Eva Novotny called Stellar Atmospheres. I know it well. Okay, because one of my projects I had to do was to actually build a star on the computer,
Oh,
a working star, so that
that's interesting.
when you hit go, you got a image, a layout of all the reactions going on at the same time in your star, and from the core all the way to the outer envelope of the star to the edge, so to speak. You had to have all the right numbers to show that you built the correct star.
Oh,
My
that's
star.
neat.
Yes, I had a cool star. All right. So it was kind of neat. Now, and depending on what kind of star it is, well, different things happen. Okay. So, for example, you can see my cursor here. Up here, you'll notice there's a snaky line right here. Okay. Now, that snaky line is interesting because those weren't just placed there. This came out of a direct observation of looking at a whole bunch of stars and then plotting their brightness, okay, in terms of brightness of the sun. So like
Right.
100,000 times the brightness of the sun would be here, 1,000,000 times would be here. Okay, versus the color of the star. Now, one thing we learned early about stars is that the color directly relates to the temperature of this outer region of the star. It doesn't relate to the core too much, but you can theorize a rough calculation. But let me give you this. Okay, the blue stars are extremely hot. Blue hot is the hottest hot there is.
Okay.
Okay, and red hot at the other end here, which if we touch a red hot thing, it's going to just give us 3rd-degree burns.
Right.
But in terms of a star, red hot is actually fairly cool. Okay, this might be 60,000 degrees, and this might be maybe 5,000 degrees. Okay, so the big difference, and it goes from blue hot to red hot, and that's in Fahrenheit. If we talk about Kelvin, well, this might be 25 to 30,000 Kelvin, and this might be about 2,500 to 3,500 Kelvin. Kelvin is another temperature scale that we came up with because we wanted to have an absolute zero instead of dealing with minus 273 degrees, because minus 273 Celsius became the standard for absolute zero. And minus 273 Celsius equals 0 degrees Kelvin. Okay. So when you talk about the difference between Kelvin and Celsius, that's a closer relationship than with Fahrenheit and Kelvin. Okay. Fahrenheit is a weird calculation. I think Celsius is a better scale to use. So
it's what you get used to when you grow up.
No, that's right. That's right. And James Dugan, I feel bad for you, James.
Oh.
Yeah. That's so she wouldn't get within the reach of your arm, so you could hit her back.
And I'm sure James was a good kid too, just like you.
Yes, he was, I'm sure.
Very inquisitive.
Yeah. So anyway, and Michael Hedrick says this is "Oh, Be a Fine Gal, Kiss Me." What is that? Do you recognize that?
OBFGS, isn't that what we're looking at right there?
Yeah,
the spectral class.
Oh, be a fine gal, kiss me. Now, I'm embarrassed to say that is how we learned the scale when we were younger. Okay, there is a further end to this scale which isn't here. It's right now SMAC, RNS. Okay. And those are additional types of stars that ended up getting their own category, which we're not going to talk about tonight. All right. But that's because they're relatively rare. You wouldn't see them on this scale. You wouldn't see them too many on here. So this line going down here then is where they noticed a normal star, which was blue, and all the way down through the scale. These are all normal stars: blue, lighter blue, white, yellow, orange, and then red. Okay. As they progressed downward, they noticed, as the stars got lower in temperature and they graphed it against brightness, they found that it made this snaky line. What they discovered was every one of these stars that are on this snaky line are actually fusing hydrogen into helium like our sun is doing. It's a normal fusion process. It's the normal way that stars make energy, is hydrogen fusion. Now, they also noticed stars that don't belong on this scale. Now, interestingly, they didn't know enough about these originally, except when they noticed a star that was like one of these stars up here, one of these blue stars right here that you're seeing. Okay. When these blue stars stopped fusing hydrogen into helium, they left this line. This line has a name. It's called the main sequence. And it's denoted with a Roman numeral V or 5. Okay, so our sun, for instance, is a G, and it's a number 2, G2, and then a 5 because it's on this snaky line. So that's called the luminosity class. And you can see that with stars that are brighter, and bigger, well, that Roman numeral changes. So for stars that are way bigger than the sun, but not supergiants, they might be a luminosity class 3 or a 4, all right, a 2 even. And then for stars that are gigantic, like the star Betelgeuse in the upper left of Orion. Well, that's a supergiant, and we call those a type 1A, 1B, luminosity class. Those are just massive, massive stars. If you put Betelgeuse where the sun is, it would go
Yes.
out to and include part of Jupiter's orbit.
Mm.
Yeah, that's a big. Remember, that's a sphere. It's the biggest all the way around.
Right.
So anyway, so normal stars are on this line, and they're fusing hydrogen into helium just normally. When they stop fusing, well, they leave the main sequence and they end up in a different location, possibly up here, possibly going up here, and there's all kinds of methods that which they can get there. There's different tracks that they can use. One is called the AGB. One is called the Hayashi track. There's a lot of different ways that we've found that stars can leave the main sequence and go to different places on the Hertzsprung-Russell diagram. Now, the diagram was found by what is it? Let's see here. It was found by Ejnar Hertzsprung and Henry Norris Russell. Discovered this relationship. Okay, and the star color temperature across the bottom versus the total energy output on the left here, and that gets it on this diagram. So that's what this was about. All right. Now,
And
the thing that's
can I ask
interesting, yeah,
a quick
please.
question, if you don't mind? The
Yeah.
luminosity output, is that just a calculation, or can we as humans even comprehend what that means, that luminosity?
Yes,
Does
absolutely.
that make
And
sense?
no, that's a good question. And right here on the screen, you can see the total energy output of a star is called its luminosity, and the luminosity class is what Roman numerals associated with it. Okay,
Right.
so we have stars that put out 1,000 times the energy of our sun. Okay, 1,000 times the energy. Now, that means in all wavelengths. That means the ultraviolet. That means the infrared. That means the visible light that we see. Some stars give off radio waves very well. Our sun has radio waves it gives off. I built a radio telescope to listen to our sun once.
Cool.
I'm such a nerd. Yeah. And so,
Yes, I mean,
we
okay.
have now the hotter and bluer the star, okay, the more toward the blue end of that spectrum it's going to be. So at the blue end of the spectrum out here, you're going to end up getting a lot of ultraviolet, which is just past that visible part that we see. We don't see the ultraviolet. And consequently, at the other end, when you're down here at this end, well, a lot of the star's energy is going to come off in the infrared. You're going to see a lot of infrared energy, longer wavelength light that we don't see. Like when you see what the infrared energy does to a road on a desert highway, you see the shimmering. You're looking at the air. Just a mirage there. Yeah, the mirage is the result of infrared energy rising off the road and disrupting the air cells between you and the road, between you and what you're seeing. So that ends up causing that shimmering effect that you see. You're watching the air rise off the road that's being disrupted by the energy that's reflected off the road.
Very cool.
Yeah, and that's the infrared energy that we so love, because without it, we wouldn't be here. Okay. Yeah. Anyway, so the total energy output of a star is its luminosity. So, and that means every bit of the energy that a star can put out. Okay. And of course, the temperature is what we call the spectral class. So the spectral class of the color here, O, B, A, F, G, K, M, and the luminosity class together make the spectral type of the star. So our sun is a G2 spectral class and a luminosity class 5V, so it's a G25. That's the stellar type of our sun. It's a spectral type of our sun. Betelgeuse is an M1A. Okay, it's a supergiant. So it's a M-type star, meaning it's very cool. So it belongs down here. Isn't that odd? Okay. However, it's off the main sequence. It's no longer fusing hydrogen into helium. Okay. This means Betelgeuse was probably over here somewhere when it first started. Now, why would I say that? Because these stars, the redder they get, and these stars down here, I mean, I show them as small down here, and there's a reason, because they are small. These M-type stars down here, are only, some of them are only slightly larger than the planet Jupiter. Okay.
Wow.
Yeah. And they're very, very small. Consequently, we found a planetary system around a star called TRAPPIST-1. Okay. And there was a TRAPPIST is the name of the instrument that found it. And
Oh, okay.
TRAPPIST-1 was this amazing 7-planet system, 3 of which might be in the habitable zone for this little red star. And it's a tiny little red dwarf down here. It's like one of these. So most of the stars in the universe are these tiny red dwarfs. Okay,
Oh,
most
wow.
of the stars in the universe are these. And
Mhm.
they'll never go supernova. The only things that go supernova are these big, heavy, massive stars up here. All these stars up here can go supernova. These guys, they don't go supernova. Not when they're on the main sequence down here like this. So
Mhm.
that said, these cool red stars down here in low temperature, TRAPPIST has these seven planets around it, and 3 of which might be in the habitable zone. However, because the star is so cool, all right, and so not hot, the habitable zone, the zone where life could exist and liquid water could be on the surface because the temperature would be just right, Goldilocks and the 3 bears, okay, that temperature zone is way closer to the star because they're only putting out like a 100th or less of the energy of our sun. So imagine Earth is 93 million miles away from the sun.
Mhm.
Okay. And this, if the sun was suddenly became a red dwarf star right now, we would be out of existence within a week or so, maybe 2
Oh,
weeks,
wow. That
because
doesn't take much time.
we'd be far out of the habitable zone of that red star.
Oh.
The habitable zone for the red stars, like TRAPPIST-1, is well within the orbit of Mercury to the star. All the planets in TRAPPIST-1 are within the orbit of Mercury.
Wow.
Okay, every one of
That
them.
sun must look huge on the horizon.
It's a bigger star for sure, but then again, remember,
Mhm.
it's smaller to begin with.
Well,
Okay.
perspective, remember.
Yeah. So keep
Okay.
in mind that
Mm.
several things happen when that happens. When you're that close to your star, okay, your year is going to be a little bit faster. Why? Because when you're closer to a star, you have to orbit the star, go around the star
Mhm.
faster, okay, in order to maintain your orbit. So as the physics settles in during formation, you'll find a speed at which you're traveling around the star, and that'll be stable, okay? And for stars like that are small stars, we don't measure that in hundreds of days like us, 365 days around our G-type star here. We measure that in sometimes hours.
Wow.
Yeah. And on
Wow.
TRAPPIST-1, we're looking at planets that go around the star anywhere from just a couple days to about 7 days. That's
Mm.
the on TRAPPIST-1.
If you were standing on the surface of that planet, would you feel as if it was going fast like that?
No, you wouldn't notice a darn thing. The only thing you'd notice is
Huh.
that the planet doesn't spin on its axis. You'll go, what? What are you talking about, Mark? Well, when you're that close
Oh.
to a star, one of the other consequences is that the star and the planet become locked like the moon is
Mhm.
to the Earth.
Right.
And so that's called tidal locking. And when those stars and the planets that surround them, because that habitable zone is so close to the star, the planet being in a habitable zone around a star of that minuscule size means that the planet is going to be locked facing one side toward the star. So it's going to go around the star, and it's going to have the same face facing the star all year round. So you know what that means?
Well,
Real estate boom. You sell people on a beachfront property, you can send them to the sunny side of the planet.
uh,
Take a shuttle
that's
to the
funny.
Terminator side where it's half day, half night, that perpetual sunset side,
Mhm.
and people can take pictures of sunsets.
That's where I'd live, I think, on the Terminator, I think.
Yeah.
You
And as
know?
you'll see, that probably makes the most sense for any life. Okay.
Huh.
So yeah, so what's happening is you can take beautiful pictures of the sunset. All right. You can do a beach trip, go to this Terminator, take some sunset pictures. You can spend there like weeks there taking pictures of the sunset because it doesn't ever
Mhm.
change. And then
Wow.
if you want to study the stars, you can go to the night side where you can watch the entire year of stars go by as you go around that star and look out at a different set of stars every
Ooh.
single moment. And by the time, say, 3 or 4 days, 5 days is done, you'll have seen the same stars coming back again because a year passes so quickly on those planets.
That'd be neat.
Yeah, yeah. So
Mhm.
that's kind of cool, you know. So
That's interesting.
yeah, so that's the problem with these small little guys, right? I mean, these small little planets, small little stars. You know, you're going to have that tidal locking going on.
That's not the type of planet we're looking for, is it? If we were to expand into the universe?
Well, when we expand into the universe, I think we'll settle for any planet that humans could survive on. Okay.
Fair enough. Fair enough.
However, we would ideally like a planet that is suited for human life. And what do we mean by that? Well, G-type stars are suited for human life. Yes. Now, when I got my degree in astronomy, exoplanets were the thing that I focused on after school, and
Neat.
we discovered that A-type stars on down are probably the ones that could have planets. Habitable
Mm.
worlds might start in the F range and certainly go down into the M's. Okay. A-type stars could have planets, but they probably wouldn't be habitable. They'd be still too potentially warm for that. But you never know. There's many different ways. You know, many different ways that could flesh out. However,
Yeah.
I will say that when you look at the different types of the stars, all right, the G-type star, we know that it works for us. And guess what? G-type stars might foster life on Earth at 93 million miles away. Okay. However, our planet is not the best one for life. It's habitable in spite of the fact that it's trying to kill us every moment. We have tectonic plate activity, which causes earthquakes, which causes people to be killed. Crustal plate crumpling and technology that we can't even hope to have to control it is manipulating us every day. Our oceans are very deep. Our oceans have their own problems. The hydrothermal vents on the bottom of the oceans spew lava out, and sometimes that stuff comes to the surface, makes new islands. You don't want to be anywhere near it. If you were, you're going to get fried. You know, we have tornadoes, we have hurricanes, we have all kinds of issues. The universe trying to kill us with the way the Earth is evolving and eroding and doing its stuff. So it's a constant battle to stay alive here on planet Earth, right? You're hearing about
Yes.
people that had problems with hurricanes and tornadoes and earthquakes, and it's like, wow, you know. Now, if Earth was super habitable, then perhaps our tectonic activity would have ceased. Let's say,
Oh,
and then
okay.
we'd have just a world that has no earthquakes and no volcanoes. Now, volcanoes are pretty. All right, I actually love volcanoes. They're really cool. When you learn how they made the Earth's atmosphere, helped make the Earth's atmosphere, you say, glad we had them at some point, but we don't need them now. Okay, so all that stuff though makes Earth habitable, but not super habitable. There are super habitable planets out there, and there's a few candidates that we've found that might be more or less habitable. I don't know about you, but I'm in no hurry to move.
No, not necessarily, but isn't that probably where our future's headed?
Most likely.
Possibly.
The other thing too is
Yeah.
we're running out of space on our planet too, right? I mean, as big as it is, there's many places we don't understand still. But then again, we're not in the deep ocean. If we're in the deep ocean, we would be seeing new species all the time, and we actually do find new species every year. You know, every year there's new
Yeah.
fish, new microbes, new creatures found in the deep ocean.
That's amazing.
We didn't know about hydrothermal vents until the mid 70s or so, theorized. But then in the mid 70s, you go down there and you see that this mineral laden water is 900 degrees Fahrenheit spewing out of these chimneys. Now, wait, 900 degrees is well above the boiling point of water. Yes, it is. But the pressure of the water above, thousands and thousands and thousands of feet above, keeps it in solution and doesn't let it boil.
Oh.
Boiling is a product of pressure,
Oh,
not as much temperature. For example,
I don't know that I realized that.
yeah, I have a vacuum chamber here, and I took a cup of water, put it in the vacuum chamber, sealed it. Cup of water, I put my finger in it, yeah, no problem. And I took the air out of it, and the water started boiling at room temperature. Okay.
Huh.
Yeah. And so
That's really cool.
it has to do with pressure. Okay. If we increase temperature, that can induce the boiling process, but with the temperature would be at a certain pressure, and that pressure is 14.7 pounds per square inch, which is every square inch of your body is being pressed by 14.7, almost 15 pounds. Every square inch of your body, everywhere, is being pressed by the weight of the atmosphere over your head all the way to space. Isn't that
That's
incredible?
interesting. Yes, it
Yeah.
is. But the ocean's much more than that, right?
Yes, it is, because you have the 14.7 pounds per square inch all the way to space over the ocean, and then you have the ocean water itself weighing down on you.
Right.
Which is why you can have 6 tons of pressure deep in the deep ocean per square inch.
Wow.
Yeah. Now, if we could breathe liquid, and that was an experiment they did with the Navy. If you saw the movie The Abyss, there was this super saturated oxygen liquid that they had, and they dropped a rat in it, and the rat was struggling, but it still is alive because it was able to pull that stuff into its lungs and circulate it back out. All right.
Yeah.
And if you think about it, once the lungs were full, and once you fill the sinuses and the ear canal behind the tympanic membrane of the eardrum, well, then you could literally go to the deepest part of the ocean with your body, or at least much, much deeper than normal. And if you could do a liquid breather, then all of the airspace in your body would be filled by liquid. And if that was the case, then you could literally live in the ocean and not worry about the pressure on your body until you get very, very deep.
Right.
Okay.
Wow.
Yeah. And
I think it's taking that first breath would be tough.
That's why when they were experimenting with it, the helmets that the divers wore actually pumped the stuff in and pulled it back out. They pumped it in, and yeah, I know, huh? You literally you have to drown yourself so you can live.
How scary, but that's how cool. It's like a really good ride.
It's a really good ride, except that the ones that were experimenting with this, nearly all of them developed very serious pneumonia after, because liquid in the lungs could not be fully expelled. So long recovery time. So they didn't play around with it too much after that. It just wasn't for us, not for humans,
Right.
So
interesting. Cool.
Yeah. So here on the Earth, we know about pressure and so forth and how that works. So we know that we couldn't survive in the deep ocean without something around us that can support the pressure, right?
Right.
Well, in the heart of a star, the pressure is so high that we would be literally crushed out of existence, and so but that pressure is what's needed to start hydrogen fusion, because when you have a lot of pressure on the central, and again, you got massive, all this gas around the star, and we think of gas as not weighing too much, but stars are big. The sun is 864,000 miles in diameter. Let that sink in. Almost a million miles in diameter.
Oh my goodness.
That's a diameter now, not a radius, a diameter.
Right.
Okay.
Wow.
So all that mass is focused at the center. All of the forces of the gravity are pushing toward the center. Well, when you squeeze something tightly in your hand and squeeze really tightly, you notice what? The temperature increases.
It gets warmer.
It gets warmer because you're squeezing the molecules closer together, and they're fighting it and pushing back, and they're vibrating faster, and you're making heat. Well, in the same way, when you squeeze the center of a star and there's hydrogen gas, because the star is made of mostly hydrogen, when you squeeze hydrogen gas together in the middle of a star, then you reach a certain point where the temperature is now going to assist with a process that was before this unable to be accomplished, and that was to fuse hydrogen nuclei into helium nuclei. You gotta,
Wow.
yeah. I'm doing a talk in Colorado this weekend. I'm going to Cripple Creek this weekend.
Ooh, cool.
Yeah, I'm
Oh,
gonna.
it'll be beautiful.
Yeah, and probably chilly, but I'm gonna be.
Yes,
Well, you just came back from Colorado.
I did. I did. And it was cold. We got some rain and hail
Phew.
and some sunshine. So it was
Wow.
great.
Well, but the thing is, when we squeeze the center of a star, all right, you get to the point where the temperature gets so high that another process that was well known in physics begins, and that's where you can slam another proton into an atomic nucleus, all right, and it'll stay there because the pressure is pushing it in, and then that proton and that other proton will basically glue together due to a little particle called a gluon. Okay.
Oh, that's convenient.
Convenient. And then you have a helium atom. All right. This is really, I mean, there's about 20 steps in this process. At the very top, you have a hydrogen atom pair. And at the bottom, you have a helium isotope. Okay. That is a helium atom that has a neutron in it. Okay. Either way, we've gone from hydrogen to helium. So that's fusion.
It's amazing.
And that fusion process, that first fusion process, is called the proton-proton process. Okay, it used to be called a chain, but it's not really a chain. It's the proton-proton process. Okay, the PPP, triple P. Okay,
P cubed.
yeah, it's exactly right. Yeah, the 3P process, the P cube process. Oh, we started something here.
Yeah, I love it. Love it.
And that requires a lot of temperature and a lot of pressure. And the temperature at which that process can begin is just around 14 to 15 million degrees Celsius.
Oh,
So only about that high. So not much.
wow.
Right.
Do we really
See?
measure temperature that hot?
Yeah.
Okay.
Oh,
I
and
know
it gets
that's the
even
question.
hotter when you get up into these stars up here.
Mhm.
Yeah. So that said, and this is for like a star kind of like our sun. And by the way, our sun is sort of like a as far as size. It's not the biggest by any means. It's not the smallest, but it's not the biggest by any means. It would be fairly non-discernible from 20 light years away. We wouldn't even know it was there unless we had a telescope we
Really?
could point at. Yeah, wouldn't even see it.
Hmm.
It'd be a very, very small star, very, very less bright. So that said, the fusion process winks on as it does with all these stars in the line here. Now the difference is these stars start with a lot of hydrogen in the middle. Okay, these stars right here start with a lot of hydrogen in the middle.
Okay.
And these stars start with the same, not the same amount, but they're smaller in diameter probably. Okay, and then these stars have their own supply of hydrogen. What's interesting is the more massive the stars are, okay, the faster they burn through that hydrogen. Okay, so stars that are up here are only on this main sequence for a short period of time, just a few million years. Then they migrate off the main sequence and become these blue supergiants that are fusing different elements, all right, and making more elements that because they ran out of hydrogen, and that causes them to swell up. And when they swell, the core is contracting, causing the outer layers to bloat out. Okay, with all the excessive heat down here, it's causing radiation to spew out, pushing away those outer layers. Okay. And when that happens, the temperature drops a little, which is why when you see this here, okay, the O star, the hottest and bluest of any star, then it becomes blue, but it's a little bit lower temperature now because it's bloated somewhat. But the core is collapsing, not core is collapsing, but it's contracting. And so it's now fusing other elements because if you want to fuse, like say, helium into carbon and carbon into nitrogen and oxygen, you have to be in excess of 100 million Celsius.
Wow.
It went from like 15 million to 100 million. Okay, that's huge.
That's a big jump.
That is, and that's the mass that we're talking about here.
Yeah.
How long do we go before the break?
We have about 2 minutes left.
2 minutes. Okay, thanks. You can just stop me and say, "Mark, shut up." I'm ready.
2 minutes. Get your show together.
2 minutes. Get your stuff together. Yeah. All right. So So this diagram then has become the staple in astronomy. We look at this diagram and say that this diagram, this is what we look at the sky with, and we use this to classify our stars. Their classifications go so far beyond this; it's incredible. Okay, and of course that's where our sun is.
There we are.
Now,
Hi.
this is our sun. All right. Now, the sun is not just a simple ball of gas. All right. The sun has a core. Right. And you can see right here, you can see it has this internal structure, and the core, you see that little guy right there?
Yes.
That's the core right there.
Blue, hottest part.
Yeah, that little hot core right there. So you might say, well, wait, what's all this? What's all this out here? Well, okay. There's a hot core in here. All right. And that core is radiating out energy, and it radiates out like for a certain amount of distance. All right. And then, like a boiling pot of water, the gas that's out here is now just getting hot, and it's cycling around, and it's swirling like a pot of water.
Boiling, sort of.
Yeah. And that's called a convective layer, convection, like we see a pot boiling.
Cool. Yeah.
Okay. And when we look at the sun, sure enough, we see these solar granules, these granulation, and they're boiling up from within and they're getting hot, coming up and going down the sides. And you see little dark rings around, little dark edges. Those dark edges are the cooler, relatively cool gas. It's still hot. Okay. It's still hot. On its own, it would glow red hot, but it's still against the much brighter and hotter sun there. It will do that.
That's cool.
Yeah.
Time's up.
Yeah.
Perfect.
Yeah. So when we come back, what we're going to talk about is the structure of the star a little bit more. And then we'll talk about something with the eclipses as well that occur when our moon passes between us and the sun. See you in a bit.
Cool.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you'd like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
Now, welcome back to the second half of the show on SkyTour Radio. I'm Mark
Yes.
Antonio. That's Tara Diulis down there.
Hello.
And for the second half of the show, Tara's going to take over
Yes.
and tell us everything we need to know.
Don't scare everyone away, Mark. Come on now.
Well, it wouldn't scare anyone. They'd probably love to hear from you. I talk too much as it is. You know that.
No, this is really cool. Very interesting. And you say it in a way that we can follow and understand. So it's great.
I have so much going through my head that, I want to say everything, but I have to try and focus. And that's hard sometimes.
Yeah.
Like,
we appreciate you focusing, and it helps. Sometimes it's so much.
It is a little, and it's like I talk about the core here for the sun. And I want to tell you about the shells that are around larger stars and the shell burning that's going. I can't tell you about that stuff because then you won't understand it. And it just gets too heavy because you need more knowledge to get to understand that part. So I'll back up a little more and talk about what happens when hydrogen is no longer there and helium has to burn into carbon and carbon into nitrogen, oxygen, into blah, blah, blah. All the way up to iron, which is number 26 in the periodic table, the highest number that a star can make. Yet the periodic table's got 118 elements. Where do those come from? And then I will probably just say, I just can't do this all in 1 hour. You know what I mean? So
I think you just did.
I have to pick and choose. Now, here's the interesting thing. Okay. I will say this. And you remember, you interrupt me whenever you want. Okay.
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 Thank you.
All right. This is the core. The core is between 15 and 20% the size of our star. Literally. Let's say 20%.
Okay. I can visualize that. Yes.
Okay. So 20%. What's the rest?
It's stuff being from the fusion. Is it just reaction and stuff that's left over from that reaction, or
not left over from the reaction, but stuff that the star was made with?
Oh, that's just there anyway.
Yes, it was.
Okay.
It's along for the ride.
Yeah.
This hydrogen gas out here. There's calcium here. There's magnesium. There's potassium. It's all the stuff that the star was made with. And remember when I talked about finding a sibling to our star?
Mm-hmm.
The composition, the amount of iron that was in our star, the amount of calcium, the amount of potassium, the amount of magnesium, and the amount of helium, etc., that was in the star. It was in this envelope. This envelope, the stuff around the star's core, that's what the star was made with. And so that's a very unique composition. All right. The only stars that will have that exact same composition are the stars that were formed with us in the same nebula.
Wow.
And that's how we can find our stellar siblings.
From going 20 times around the galaxy and having been split apart.
That's exactly right. Over time. You're right. You can see it.
Is there a filter now? Is somebody putting a filter out there into the universe looking for those exact elements that our sun has?
Well, there was a program to do that. And the one sibling we found so far, it literally looks just like the sun. When we look at the spectrum and those dark lines we see, okay, now I got to explain how those dark lines occur, and I'm gonna.
I sidetracked you.
No, you didn't, because that's how we find our siblings, is by looking at those dark lines. Okay. Yes. Now, when we look at those dark lines, those are called absorption lines. Now, what that means is, okay, when we look at the core is very, very, very hot. It's the hottest part of the star. Okay. So we're looking at that hot core, and in that hot core, what's happening is the temperature is much, much hotter by millions of degrees than the outer layers here. So considering how hot the core is, this gas out here, which is so hot that it would vaporize you immediately, okay, is still much cooler than the inner core of the star. Okay, so when you get radiation coming through this envelope, these nuclei that are out here, there's no atoms out here. It's all atomic nuclei, free protons and electrons. That's called plasma. That's all we can get out here. It's too hot here for atoms to form. Okay, in our star, right? Other stars, they're big enough that they're cool enough on the outside where you can get atoms to form. Not our star. Our star is like most others, where you just have free protons and electrons running around, as I said, plasma. And so when this radiation goes through here, okay, what happens is these nuclei and the electrons that are all free are absorbing some of the energy that is
Okay.
through them. And depending on what kind of atom and nuclei it is, if it's a proton and it's hydrogen, if it's several protons, maybe it's two for helium, etc. Okay, and so these protons and the electrons will absorb some energy, and depending on what it is, if it's oxygen, it's going to absorb a certain amount of energy, but it's going to absorb it in the same exact way because it's oxygen. Oxygen
Mm.
absorbs it exactly one way, hydrogen another way, magnesium another way,
Okay.
phosphorus, calcium another way. So you
Hmm.
actually see the lines in the place you expect to see them. We can actually catalog where the lines are supposed
Oh.
to show up. And so we can classify a star by looking at its spectrum, which looks like this for a bunch of different stars.
Ooh, it's so pretty.
See all the dark lines?
Mm-hmm.
Yeah, those dark lines are
Interesting.
these absorption lines. If we go to Alpha Lyra, right? It's right here. See Alpha Lyra?
Uh-huh. Yeah.
A05. So actually, Alpha Lyra, that's called Vega, that star is a standard for us. That's a standard star that we use for spectra. And it has the strongest hydrogen lines, which you see right there in this row. You see these vertical dark bars.
Mm-hmm.
Those are the very, very powerful and strong hydrogen lines in the A0 star. You can have A0, A1 to A9, right? You have O0 through 9. You have G0 through 9. We're a G2, okay?
Okay.
And that's just the color. That doesn't have anything to do with the luminosity class. We're not talking about that. But for a standard star like ours that's fusing hydrogen into helium, which is what Vega is doing, it's an
Mm-hmm.
A05, okay? And an A05 is this guy right here. That is the first star in the A-type star, all right, category in that class. And then the 5 means that it's fusing hydrogen into helium normally. And they are characteristic because they have these strong hydrogen lines.
Hmm.
So these are characteristic stars you see here. And every single stellar class has these, okay? For instance, here's another diagram
Oh,
showing you,
okay.
okay? As we move down, you can see again, there's the A0, okay? And you see the A0 has those broad, dark
Mm,
hydrogen lines. You'll
yes.
notice that they seem to fade out over the course of the distance down toward the M stars. And you notice it down near the M stars and M2 stars, right? Actually, starting with the G stars, G5 and
Yeah.
G0, and even in the F5, you can see there's more smaller lines throughout there. You see that?
It looks darker. Yes, it's a lot.
Yeah,
And that's because there's more lines.
there's more
Mhm.
lines in there, and that means there's more elements that are showing up in the
Okay.
spectrum there. Okay, and the M stars, when they're actually so small, they can actually form molecules in their outer atmospheres.
Hmm.
Okay, and the supergiants that are the red supergiants can also do that. All right. Now these are, you can see up there they have the lines labeled. Okay, you have
Mhm.
H2 and H gamma. Those are all the hydrogen lines. Okay, and you can see helium lines out there, and He lines. You see iron 2, AFE2, Fe Roman numeral 2. Okay, and again, those are again different different uh, variations of the same atom, right?
Okay.
So when you look at that, these colors, these dark bands, are the result of I think this shows like we if we have just the sunlight, we put it through a prism, we have a continuous spectrum. Okay. Now, in a case where we have a hot gas which has been expelled from a star, and the star is causing it to glow, that's where we see a nebula. Okay.
Oh,
So the
okay.
Orion Nebula, like you did for our SkyTour live stream observatory in the Sonoran, okay, that nebula is glowing because there's a thin gas, hydrogen gas, and oxygen out in the cloud around the stars that are in the middle of this nebula, and they have a lot of ultraviolet energy, which are causing these emission lines. These emission lines are from electrons in the atoms which you have atoms of gas out there,
Mhm.
jumping off the atom and then coming back in. And as they do that, they give off light. And in hydrogen's case, it's a red light. Okay, oxygen, it's a blue, and teal green, teal blue. All right,
Mm.
and so that's what we see. And then the bottom one is what I just described to you. We have the light bulb is like the hot core of the star. The cold gas is the outer envelope around the star.
Mm.
And if we break that light apart, we can see dark lines where that cold gas, relatively cold gas, it's not really cold at all, absorbed some of the energy and made dark lines in the spectrum.
Mhm.
Okay. And that's the three kinds of spectrum. We have continuous, we have absorption and emission spectra. And
Very cool.
yeah, and so we see tons of lines, dark lines, tons of absorption spectra in our star here. And these lines have they have a name. It's called the Fraunhofer spectrum, and we can identify all these many elements in our solar atmosphere. And if you think about it, only a star with that exact same composition would look just like our sun in the spectrum. The intensity, the brightness of the dark line, thickness of the dark line, the whole 9 yards. And that's exactly what we found with this sibling down in the southern hemisphere. So our listener down in Perth, okay, now knows that we have a twin down in the southern hemisphere.
That's awesome. So do you think all of our other planets are still fairly close to us, and that we'll find more than just
You mean
one other?
the stars?
Our siblings, yes, our siblings.
Well, the southern hemisphere, it just means it's in the southern hemisphere. It could be many light years away.
Mhm.
Okay, because we've gone around all those times around the galaxy 20 times or so, and they have scattered quite a bit. I forgot how far away it is. I probably should have looked that up.
It's all good. It's far.
Yeah,
It's in a galaxy far, far away, I think.
No, it's in our galaxy. Here.
Oh, okay. That's the kind of the confusion, that it's in our galaxy, or is it somewhere else, but that, of course, it's in our galaxy. So
Yeah, it's in our galaxy. I mean, we have anywhere from 150 billion to 400 billion stars. And you might say, why can't we just count them? Well, if you look in our galaxy, you'll notice that there's lots of dark stuff in our sky when we look at the night sky, right?
right.
And here's an example I showed you before. Okay, you look there and you can see dark splotches amid the bright stars. That's dark dust that's obscuring our view beyond. And we're in the disk of the galaxy, so we're inside a forest.
Yeah.
And from inside a forest, you can only see so far before the trees block you from seeing anything beyond. And that's kind of what we're in the situation here in our galaxy. We're sitting in this beautiful spiral galaxy, which turns out isn't even a spiral. It's a barred spiral. It's got an extended nucleus with spiral arms off it.
Oh, cool.
Okay. Yeah, I know, right?
Yeah.
Who knew?
And
yeah. And this barred spiral galaxy that we're in is hiding the rest of itself from us on the other side of the galaxy. We're on one side of the galaxy. We can't see past the bulge of our galaxy, which you see right there, down near the bottom there, just above the horizon. You can see it getting a little wider and then it gets a little thinner. That's the central bulge of our galaxy.
Huh. Okay.
Yeah. And here's a galaxy, for instance. This is a spiral galaxy called Messier 101. And we image this. Now, the reason we image this is because we caught this supernova. This here's a star that obliterated itself, the one with the little red markers on it. Okay? Yeah, that points to a star that went supernova, and they last for several weeks, and then they die off, and then you'll never see them again. But that's in this galaxy, and you'll notice that in this particular image, if we were in this galaxy, you can see look at the central bright bulge, and then just to the right of it, you see a spiral arm which kind of curls down. Okay.
Yes.
Right, curls down. Right. And then just past it's another spiral arm that's curling down. Okay. That's about where we would be. And you can imagine if we're looking through the galaxy's center, we couldn't see the stars at this side of the galaxy, up top left of the galaxy. we wouldn't know what's there. We have this blind spot, a huge conical blind spot we can't see through because of all the dust. And we're in the middle of all the dust inside the arms of the galaxy, which is where we are. Research indicates we might actually be in a bunch of dark dust, actually, that encompasses the Pleiades. Now, everyone knows the Pleiades, right? I mean, you know what the Pleiades
The
look
Seven
like.
Sisters, is that right?
Yes, that's correct. The Seven Sisters. And the Pleiades are beautiful, but they are also something that have a lot of dust around them. And when you look at them, they have dust surrounding them all the time. And the dust that surrounds the Pleiades, they're 400 light years from us. Sounds like it's far away, but it's actually close galactically.
Wow.
So that dust may extend to us, and we might be in the middle of all this dust and not even know it. We might be seeing what we can see because we're seeing through the dust.
That's just so cool
to
think about. Interesting.
My personal feeling is that it's affecting how we gauge distances to objects. Because when we look at objects that are far away, they seem redder to us. And we call it interstellar reddening. And that's because there's dust between us and those distant objects, and it reddens the light. In the same way that looking through more air at sunset makes the sun red. The sun's not changing color. The sun is actually white. In space, it's white. It's not yellow. But in our sky...
right?
Huh?
Is that the plasma glowing?
Well, yeah, you're seeing the plasma in the outer atmosphere of the sun. That's right.
So,
But it's really a white star, pretty white. And we say it's yellow, but it's yellow because we're seeing the light of the sun through the atmosphere, and it's reddening the light because some of the blue light is getting scattered out of the spectrum. Now, we talked about this generic spectrum here: red, orange, yellow, green, blue, indigo, and violet. Well, the blue light at that far right end there, our atmosphere and the molecules in our atmosphere, they're kind of tuned to that light. They'll absorb it and then shoot it out in all directions, leaving only the red parts, the red, orange, and yellows, to come to us. So that's why during the day, the sun at the height, when it's noon, still kind of looks a little yellow. But at sunset, we're looking through more air, so more molecules are taking and scattering more of that blue light, and it makes our sunset look red.
Beautiful.
Yeah. And so that explains why the sun changes color, but it also explains the possibilities for why when we gauge distances to things, we look at them, they're far away, we're seeing them through more interstellar space with more interstellar hydrogen and interstellar dust out there. And so we'll see reddening occur. We'll see that the objects get reddened the further away they go.
Yeah. Well, that's just the dust in the atmosphere affects that too on the sunset, right? So
that is correct.
The dust in the space would be the same.
Yeah. Molecules of oxygen and nitrogen in our atmosphere will also do a scattering of the blue light. Dust will scatter the blue light as well, very effectively, which is why when there's a fire, sunsets are scarlet red and not just orangey red. They're scarlet red. Yeah. See, that's cool. So there's a number of reasons and a number of things that we've learned about the sun. And, there's a few things, and we're going to talk about little of these other things too here, but I wanted you to see the core first. The core is about 20% of the sun, and the rest is along for the ride.
That's neat.
Yeah. Now, the surface you see, if you look at it with a telescope that has a solar filter on it, this is the surface you see. See, there's a sunspot over here. See that?
Yeah, there's a couple of them. It looks like,
there are a couple spots. And you see this looks sort of modeled here. There's a little tiny spot here, a little tiny spot there. And you'll see there's a little dark area kind of here, and then this is a lighter area. But you notice when you're looking at this, you're seeing the surface of the sun has like a texture to it. Kind of looks a little rough, doesn't it?
It kind of does look like a ball, like a harder ball, like a gumball maybe surface.
Yeah,
a jawbreaker type of thing,
Yeah, it looks like it has a surface, doesn't it?
Mm-hmm.
Okay. Well, this is where I have to blow up everybody's brains here. Okay.
Great.
If you head toward the sun, okay, visually we see this edge here. This looks like what we call the photosphere.
Okay.
Now it's 93 million miles away. As we get closer and closer and closer and closer to it, this sharp edge will change into a gradual
Wow.
variation, a gradient going from brighter to dimmer. And you could be traveling through that photosphere on the edge and not really know that you're in it, except the temperature would be rising outside with the few atoms that are and molecules, or sorry, the few elements that are the nuclei that are striking your craft. You would be getting pretty warm. The Parker Solar Probe was zipping through not the photosphere, but the coronosphere, the outer atmosphere of the sun. And so, as you get closer, you're going to see just like a cloud looks like it's a sharp edge till you get close, then you can't see the edge anymore, right?
Oh, that's
Because you
cool.
realize you're so far away. Then when you get closer to it, you see that it's actually much softer edged.
Hmm.
It's not the sharp edge cloud you see from back here. And that's what we're seeing with the sun. The sun's edge here would not be sharp when you got to it. It's not like you can go stand on that.
It kind
Okay.
of reminds me of it's similar to like smog or something. When you're coming into a valley or something, you see the edge of the
Yes.
atmosphere kind of, and it's I don't know if that's a good analogy, but it's not as when you're in it and when you come down into it, you don't even realize you're in it, but you
That's
see
right.
it when you're coming down
Exactly
into it.
right. It's like
Mhm.
passing through a cloud in an airliner. All of a sudden you see the white becoming more and more and more, and then it's gone again, but it's not like
Yeah.
instant. You don't go into a sharp edge thing, boom, now you're in this cloud, then boom, you're out of the cloud. It's gradual onset, gradual receding, gradual receding.
Cool.
So that's kind of what we're looking at here. It's just that photos of the sun from a long distance, we see an apparent disk. Okay, now here's another view.
Cool.
Okay, this is a sunspot right here. Obviously, this
Neat.
sunspots are interesting because these are areas on the sun where magnetic field lines are getting twisted up. The sun has a very powerful magnetic field, the most powerful magnetic field in our whole solar system. So the sun's rotating on approximately a month basis. It rotates, once on its axis. Okay, revolves on its axis, and as it does so, it has a magnetic field. But as it's moving and rotating, it's a very massive ball. Those magnetic field lines get sort of dragged out. So as it rotates around, they get dragged out around the equator of the sun, and it takes a while for that to occur. But sometimes they'll get to a certain point where they'll break, and when they break, this happens. We see a momentary blob show up on the surface of the sun. That's called a sunspot. Sunspots can be this sunspot right here is way bigger than the entire Earth.
Oh my goodness.
Yeah, this is way bigger than the Earth right here. The Earth actually is only about this big in this picture, maybe about like that, if that. It's smaller than the width of the arrowhead.
Huh.
Okay, yeah, and this is a broken magnetic field line, and as such, it's a turbulent place. Now, why is it dark?
It's colder.
Very good. That's exactly right. Wow. I thought I was going to have to coax that out of you, but you knew.
Is it colder because the magnetic has stretched out and it's in the atmosphere and not as close to the sun? And
close. The dynamics of the sunspot are that it's actually a little cooler here because of the way the radiation is moving in the spot. So it is a little colder. And we say cold, people think, no. If you took this sunspot off the sun and put it out in deep space all by itself, it would be red hot. And you'd be like, whoa, you can feel the heat from here, kind of a thing. But because it's on the sun, which is even hotter, it looks dark against the brighter sun.
Funny. That's strange.
It's still a very bright object in and of itself. And yeah, you see, photography is kind of weird, but you can see this modeling too. See that modeling you're looking at there?
Yes.
It doesn't look smooth.
It looks like noise on some of the pictures you take.
It does. It does. Here's another one. Okay. Again, this is the photosphere. This is the surface you see if you just use your eyes with a filter. Okay.
That's neat.
This is photosphere, but it's got a bit of hydrogen alpha in this, which is a a wavelength that the sun emits that shows us different details in the sun. See these
Mm.
things right here? Okay, we have these beautiful
Oh,
sunspots
yes.
here.
Mhm.
Okay, this is a relatively active sun. Now, once in a while, it's in these sunspots where flares originate. When we get a solar flare, if there's a sunspot group of any note, they could have a flare which will emit a lot of energy. And if it's facing us, it could come right toward us. Okay. Okay. So here's a close up, and you can see that boiling pot effect I was telling you about out here.
Yes.
See
Ooh,
this?
that's
Right out
so
here on the outside.
cool. Yes.
Okay. This is the penumbra. It's the lighter area of
Mhm.
the sunspot. It's hotter. And the coolest part of the sunspot is here. It's called the umbra. Okay. It looks like hair, doesn't it?
It does. Those are very artistic terms as well. It's very organic, but that's a real picture?
It is. And here's what's
Oh,
interesting.
wow.
If you were to look at this, okay, these these hairs right here, what look like hairs, they're following magnetic field lines. So
Oh,
if you saw them from the side, it wouldn't look like this. It's like this. Okay.
yeah.
So that's arcing over and going down. And so these are going down into a cooler region. Okay.
And Mark, it sounds like it's liquid. It sounds like liquid, but then you identified something that it breaks, and that's kind of an interesting analogy too.
Oh yeah,
So,
yeah. It's the magnetic field that is suffering here. So what's happening is in this area, if you can look at the magnetic field going on here, we've got magnetic field lines coming out of this thing. There are magnetic field lines that have, uh, remember that as the sun's rotating, it's twisting up the magnetic field lines. And if they
yes.
get twisted at just the right amount, they could break and form thousands of additional little magnetic field lines for the moment. And they'll spiral out and shoot out. And that's what we're seeing here. Okay.
Mm.
Um, and so, certainly some are coming out, some are going in here. And this is an area, for instance, where you'll see prominences, those explosive things coming off the sun. It's not only place, you can see them all over the sun, but you see also here, since it's very turbulent, inside here, you could get a solar flare that just erupts and becomes a bright, bright
Oh,
flare. And it's from these guys, you'll see things like coronal mass ejections. This massive stuff is just shot out. And it comes toward the Earth. And when it hits our Earth, it hits the magnetic field first, spirals around the poles, comes in, makes beautiful aurora borealis. Okay, we saw some at SkyTour Sonoran,
yes.
and I even have the overnight video of that showing these beautiful auroras that occurred down in Arizona. It's very rare to see
Oh, yes.
auroras down that far south, you know. So
Well, you
that's
saw them
the
in Connecticut too, didn't you?
oh yeah, in Connecticut it was just
Mhm.
incredible. Yeah, in
Yeah.
Connecticut it was far better than Arizona, but here we had a freaking aurora party.
That's cool. So
Yeah.
is the magnetic field comes first before the sunspots and the solar flares, or
Well, the magnetic field is always there in the sun. And as the sun rotates, its magnetic field lines get twisted. Now, what do I mean by magnetic field lines? Are they actual lines? Okay.
that break?
They're lines of force. Okay. So
Or
if you take a bar magnet and you lay a piece of paper on top of it and sprinkle iron filings,
Mm.
they don't just go to one end and the other. They actually make a pattern. You see a pattern. From the North Pole to the South Pole, you'll see a pattern of lines that appear. These are magnetic force lines that you're actually looking at, the magnetic field lines. Okay. And when you talk about those breaking, imagine if you twist the magnet enough so that those lines they don't know where to go at a certain point, and they break and then they reconnect. And because the sun
Oh,
is so
okay.
massive, the break and reconnect, okay, that we're seeing right here takes longer. Okay. So the lines are
Interesting.
breaking and reconnecting, and this is what's going on
It's like
here.
pulling a magnet apart and it wants to come back together real quick.
Sort
So
of, kind of, yeah, exactly.
Mhm.
But the magnetic field lines are the
Beautiful.
things that are getting twisted and moved around. Now, the sun's magnetic field is staying the same as the sun's rotating, but the field lines are getting dragged around.
Mm.
All right, and that's the part that is causing all the turbulence on the sun. Here's another major spot.
Wow,
You
that's
notice,
beautiful.
you see this shapes down here, all these little tiny little cells you're looking at. Okay, there's this granulation here.
Oh,
If you
there's your
see, this stuff is like these little tiny granules. These are well, they're called granules. They're areas like of a remember I said the outer atmosphere of the sun's like a convection pot
Mhm.
of convecting water. Well, these are the convection cells. They're just tiny. So here is a bright one right there, and around the edge of it is a rather dark ring. Okay.
Right.
And you see more of them, and you see all the dark outlines around the bright centers. And that's the material in the center coming up and then cooling and then going down the sides, okay, making them darker. So it's
Right.
cooler by just a little bit. And that's what solar granulation is. It's these convection cells in the outer atmosphere of our sun.
Yeah. Those holes are doing the same thing to me. They're playing with me optical as the dark dust in the universe is. I want to think I'm looking at a dark hole, or looking through something with that dark spot. Just like the dust, it feels like I'm looking through the light, it's not obscuring it.
This
So
year, you mean?
yes.
Yeah.
Mhm.
Well, here's the thing. I mean, if we were to take a longer exposure of an extremely bright object like this, we'd have to close in. If we had a telescope and it's been done to just look at this part of the spot and take a
Okay.
slightly longer exposure, we would see what's going on in there, and we'd
Oh,
see the turbulent middle and things going on. But in these types of photos, we don't actually see them here because the photo was taken to show this bright photosphere with the sunspots and so forth.
yeah. That's just
Okay.
beautiful.
But it's not just black. It's actually full of material that is doing things. We just don't see it in this photo.
Very cool. Thank you.
Oh, of course. Now, so the photosphere is there. And above the photosphere, you notice this is kind of above the
Mhm.
photosphere, is the chromosphere. So above the photosphere, we have this area here. Now, this stuff on the sun is glowing in a different kind of light. You'll notice when we looked at the other pictures, like this visual image of the sun, we see sunspots. We see this quote unquote edge of the sun. What you're missing is a different type of light where these objects are visible. These are prominences. These are explosive outbursts on the surface of the sun.
Wow.
Okay.
Neat.
Yeah.
Yes.
These are every one of these that are in this image are way bigger than the Earth.
Oh my goodness.
Each singular prominence, which will last us several days. Okay. Hours to days. Well, if you look at the light of the sun, if we look only in the light of the hydrogen that's coming to us, that's it's called hydrogen alpha. Using a hydrogen alpha telescope, I have one in the closet right here,
Mhm.
okay, and behind me.
Cool.
Yeah, we're setting up a solar observatory out here, and we're going to be able to see just images like we see here on this left side.
Oh, that would be so neat.
Yeah, we'll be able to
Yeah.
see the prominences and stuff.
Mhm.
So you'll see that there's a
Awesome.
lot of detail on the surface of the sun here, right?
Yeah.
And this surface is full of all kinds of interesting phenomena. We have the prominences, we have the granules, we have this snaky thing. You know what that snaky thing is right there?
No.
It's one of
But
these things seen from above.
oh, of course.
Because
Okay.
this is cooler, right? Because it's rising off the sun, it's cooler a little bit, so it looks like a little snake. From the side, it
Okay.
might look like that.
Yes.
Yeah, yeah.
Neat.
Yeah, yeah. And the plages are these white areas where usually you see them where the sunspots are. And those are just areas of turbulence. And it's out of those we're going to see flares many times. So that's the chromosphere right there.
Ooh, pretty.
Yeah. Yep. And then we have within the chromosphere, it looks different all the time. Here are prominences. It looks like it looks like an orange that's got some kind of mold on it or something. But that's actually the sun. Okay.
Mold.
Yeah. And here's a nice view.
Ooh.
This is a prominence. Remember the snake? Well, here's another view of it from a sort of an angle. You can actually see how it's kind of rising off the sun here.
Very three-dimensional.
Yeah, and this is on the sort of on the edge, but it's coming down in here. Okay, so there it is rising off, and you'll notice again, very very hot area. This is an area where you might get a a flare potentially if there's a sunspot here. Sunspots are seen in the visual spectrum in the chromosphere in the light of hydrogen alpha. When we look at it, we're just looking at hydrogen. We see the hot spots. We don't actually see the sunspots.
Okay, but
We just
that's where
see the,
they'd be right there.
yeah, they would be kind of in that region. Okay. So neat stuff. Now, here's an example of a flare, and you'll see it's going to be right here, and you can actually see this is the chromosphere. We see it's sort of superimposed with the sunspot there. You see this right here. There's the flare, and I don't know if you saw, but there's a flare that comes off right here. Okay, boom.
Oh,
There. So this flare shot off, and it's headed right for us. It's coming right for us.
duck! Oh,
Yep.
duck and
Yep.
cover.
Yeah, so this is a time lapse. You'll notice the time on there.
Wow.
Look at the time. Okay, it started at 2 o'clock. It went all the way to about went from just at the end of 1 o'clock to 2 o'clock, not quite 3. So in the whole frame of an hour and a half, this occurred. All right, so
Wow.
that's pretty cool. You know,
That's neat.
yeah. So when the moon gets in the way of our sun, it blocks out the brightness of the sun, and the sun has a certain size in our sky. Okay, and so the top edge of the sun, you'll come down here, you'll see it passing by the moon. Okay, and then it'll go to here. Okay, and then you'll see that the top edge also will go to the bottom here and goes off to this side here. If you just follow the vectors, you can see what's going on. So because it has an apparent size in the sky, we get two shadows. We get, just like a sunspot, we get an umbra, and we get a penumbra. Yeah, and that's that right there. And so the penumbra is huge. The penumbra is huge, and the umbra is only the size of the moon's direct blocking. Okay, as seen from the Earth. Okay, there's no other light that can get to us from there. Okay, because it's completely blocked here. But here, some of the light gets here, but some of the light is blocked by the diameter of the sun. And these are not to scale, obviously.
Right.
Okay. Yeah, the moon's orbit. Yeah, the moon's orbit is also elliptical. It's not round. Okay, and it's tilted at 5 degrees to our orbital plane. So that's why we don't get eclipses every single time the moon is a new moon. You know, it's either above or below, and only where the crossing point, where the crossing of the moon's orbit, where it actually goes like right here, where it's crossing the Earth's orbit, only when that's aligned with the sun will we see an eclipse. And what's happening is, from the top, the orbit's actually doing this. It's doing this, and then it's doing this, and doing this, and doing this. The orbit is doing something called precessing. Okay, it's like the old spirographs that you could.
I was just thinking a spirograph. That's what it looked like.
Yeah, yeah. Spirographs for studies in precession. You actually see the precession of the orbit, and so the high point is here, and the low point is there. Then the high point is here. Okay, and it makes its high points all the way around over time. And when that lines up, where the crossing point to the plane of our Earth's orbit, facing the sun, when that crossing point lines up with the sun, we'll get an eclipse. Okay, and that's now if the Earth and the sun and the moon were all in the same plane, we'd get an eclipse every single lunar cycle. But we don't, because the moon is at a 5-degree tilt, just about 5, to our Earth's orbit. So and it's precessing, so we get that issue where we don't see eclipses every time. Okay, and that's pretty cool. So we get several different types of eclipses, and we get a partial eclipse. That's where we're not in the direct line of sight of that darkest part of the shadow right here.
Right.
Okay. We get an annular eclipse, and we get this total eclipse. Now, wait a minute. Annular eclipse. That's an interesting concept, because it has to do with the moon being a slightly elliptical orbit. Remember I talked about being a slightly elliptical orbit? Well, sometimes that elliptical orbit is a little closer to the Earth and a little farther from the Earth. Okay. And that's precessing, like we talked about. Okay. Well, that closer part of the orbit, when the moon is on that point where it's crossing the Earth's plane, right, where the orbit is crossing that 5-degree tilt is crossing our plane, and it happens to be the closer time where the moon is passing closer to us, we'll get a total eclipse because the moon will now be a little closer to us and can block all of the sun.
Right.
However, if it's doing its orbit and that as it precesses, if we're catching the moon when it's the farthest away from the Earth, but crossing the plane of our Earth's orbit, then we get an annular eclipse because the moon doesn't quite block the entire sun, and we get this ring of fire around the moon for a few minutes.
It is. You don't hear about those that often. I mean, obviously because they're annular, but still, it's
they do happen. Okay, and partial eclipses are more common, and again, it depends where you are on the planet too. Because you can see them as well.
But certain areas are always going to get the eclipses. Would that be? I mean, over time, certain areas will never get them, right?
No, every place will probably see an eclipse at one point or another, except perhaps Antarctica and North Pole. Okay. Here's a partial solar eclipse. There's the moon passing in front of the sun. That's an actual time lapse.
Oh, that's so neat.
Yeah. There goes our moon.
Oh, wow.
Yeah, isn't that cool? And notice, by the way, that whole time, you can see the prominences on the surface here, and they haven't changed. They haven't changed. It takes hours and hours and hours, like this one right here. Okay?
Yes.
It takes hours and hours and hours for prominences to change because they're so big and so far away. There's subtle changes, and that's about it.
Yeah, scale is
pretty
so
cool,
huge.
Huh? Yeah, the scale is huge. So here's an example. When we saw the moon's shadow, this is the most recent eclipse, on April 8th we had. I saw this one.
Is that the path of totality there?
Yes, it is. This is the path of totality. And the penumbra was out here. Obviously, the penumbra was huge, but the path of totality was here. Now, here in Connecticut, right there, that's where I am. From here to here, we're 170 miles away or whatever.
Okay.
And here, the sun wasn't totally covered, but 93% of the sun was covered. Okay. So we used glasses like this to look at it. Yeah, they're so cute. Okay. Or we could use solar telescopes. I had my solar telescope set up. We're looking at it with that too.
Neat.
All right. This is Big Bear Lake in California.
Pretty.
And there is a solar telescope literally out on a peninsula in the middle of the lake, because lake water has a way of stabilizing the solar images coming in. So they use the lake to stabilize. It's automatic.
Oh, that's interesting.
It was very cool. Yeah. Yeah. And
then, does that have to do with the mirages you were talking about earlier? I mean, does the water
exactly
it differently or something?
Yes, it allows for more stable solar images. Correct. Absolutely correct.
Interesting.
Because when the water absorbs solar or infrared energy from the sun, it doesn't radiate it away as much as asphalt would. If that was in the middle of a parking lot, the images would stink.
Interesting. That's very cool.
Yeah. So here's a total solar eclipse. Okay. And this is the one from here. This is when we had the 93%. Okay. So here you can see this little sliver of the sun showing up. So this is how it looked here from Connecticut. Okay.
Neat.
This is the moon, obviously. And you'll notice around the outside, we can actually see around here, we can see
corpuscular rays.
Coronal ray. Well, they're coronas, the outer atmosphere of the sun, the extended outer atmosphere of the sun that we're seeing here.
Wow. Yeah.
Yep. And interestingly enough, when it was 93% here, and you looked around, it looked weird.
The color, you mean?
Yes, the area around looked dim. It looked too dim, yet it wasn't dark. It's just there wasn't enough light. You felt like you're wearing dark gray sunglasses, but you could still see quite well. And there was a lot of people that just thought, there were clouds over the sun or something. They didn't even know. Okay. But isn't that something?
That's
So
really
at
neat.
93%, it still looks like daytime, and most people wouldn't know that something was going on. 93%.
Mm-hmm.
It's only when that final 1% of the sun actually gets covered that you'll see, whoa, it just got dark. And the birds are singing. The birds are singing, and the bugs are starting to come out. You're hearing bugs at night, crickets and stuff,
Right.
because they're fooled too. Yeah, so it appears to dim slightly, but it doesn't get dim enough for anyone to say, "Hey, what's going on with the sun?" They just think it's a day with a few clouds. They don't even look up.
Isn't it unusual that our planet has a moon that kind of fits the shape of the sun or the sun? I mean, the other planets in the solar system, you don't see eclipses, do you, or can you?
Actually, that's a very good point. I wanna address that, because one of the things that's really interesting is that people say often, it's kind of weird, isn't it, that our sun, that our moon is 400 times smaller than the sun, but the sun is 400 times further away. What's the deal?
It's a coinky-dink.
It is a coinky dink. Well, actually, just to kind of dispel the coinky dink a little bit, it just happens that at this point in time, that's true. But the moon, when there were total eclipses in the past, and I mean millions and millions and millions of years ago, billion years ago, when there were total eclipses then, the moon was giant in the sky. And
Because
so
it was closer,
it was closer to us.
and that made it giant, but it's the same size.
Yeah, it was the same
Okay.
size, but it was just closer to us. Now, interesting about that, if you look at the way the moon orbit has changed over the billions of years. When the moon was formed, it was actually quite close to the Earth, and both the moon and the Earth were spinning rapidly relative to each other. Rapidly, the moon was not stuck, tidally locked like it is now. Initially, when it was first formed, and where the Earth was still molten and the moon was still molten, everything was spinning. But over time, as the Earth cooled and the moon cooled, the moon was close enough to the Earth that it became tidally locked. Okay, and therefore, we had one side always facing us early on. All right, and when that happened, we had a day that was only 4 hours long. Imagine that, 4 hours.
That's faster than a Mercury day.
Yeah.
Hours.
Well, yeah.
Well,
Mercury. Mercury's day is
remember.
a very long time, because it takes
Oh,
it's tidally locked, sort of, to the sun, and takes 88 days to go around the sun.
okay.
But think about this: when a day was 4 hours here, why is it 24 hours now? 23 hours, 56 minutes, and so forth. Why is it now 24 hours? What happened? And what's going on? Why is the moon further away? What's happening? Well, we've talked about this in the past, but I'll tell you, when we look at the moon back then being so close to us, it was actually orbiting us quite rapidly. Okay. But then what happened was the Earth developed oceans, and the oceans formed these bulges, these tidal bulges, in part because of the sun's gravity tugging from this direction. Okay. And the moon's gravity tugging from this direction. Okay. Made bulges, and the Earth's rotating. So those bulges would kind of rotate. And as the Earth would rotate, those bulges would kind of lead the Earth. And that's a little extra mass of water sticking out. And far over here, okay, you have the moon. And as the Earth's rotating this way with its bulge sticking out a little bit, that little bulge is tugging on the moon over here just a little bit more. And so what that would do is cause the moon to accelerate in its orbit.
Oh.
And the moon's gravity would then be tugging on that bulge. So it would slow the Earth down a little bit and speed up the moon a little bit.
That's
And
interesting.
that process has been going on for billions of years. So the overall result is our days have been getting longer. They went from 4 hours to 12 hours to 15 hours to 18 hours to 20 hours to 24 hours now. And the moon has been going from being close to us to being at its current distance of 250,000 miles away.
Mhm.
Okay, 240,000 miles roughly, okay, away. And it's still moving outward. It just happens at this point in our history, okay, at this point in our history, the moon is at that right place where it sort of covers the sun, but it doesn't really. In an annular eclipse, it doesn't. Okay, only in
That's
a total
true.
eclipse does it cover the sun.
Huh.
So it really isn't that much of a mystery to me.
Hmm.
It's cool,
Mhm.
but it is something that we can call a coincidence, you know.
Wow.
But it's changing. It's changing all the time. Is it coincidental that you live now so that the moon is at that certain distance?
Maybe.
Or you see what I mean? Yeah. So
So
in other words, go ahead.
I say with time, it's just gonna get smaller and smaller, and it will stop blocking the sun completely, right?
That is correct.
Obviously. So,
Yeah.
and do the other planets experience total eclipses with their moons?
Yes, as a matter of fact, we look at Jupiter, and the other night using the Benson telescope, we were able to photograph Io passing in front of Jupiter. You can see Io's shadow on the surface of Jupiter.
Cool.
Io is the closest moon to Jupiter. All right. You have Io, Europa, Ganymede, and Callisto. Ganymede is the largest moon in the solar system. It's actually larger than Mercury. Okay, but
Wow.
it's a moon because it's going around another planet. If it was going around the sun, it'd be a planet larger than Mercury.
Okay,
Okay,
interesting.
kind of interesting. Yeah.
Cool. Yeah.
Yeah. See, Jupiter dwarfs things, you know.
That's why we
So,
have to use it as an increment of measurement, right? When we talk about the
yeah,
universe, Jupiter's things. Mhm.
sure. Yeah. So you see, our time and our day and everything that we tailor human life around is just based on the current state of the moon going around the earth and the current state of time it takes. Many moons have passed, many months, moon month, you know,
Right.
the names are similar for a reason. Okay. And so when we have a question about where the moon is and what it's doing, at some point in the future, the moon will eventually be able to get away from us and no longer be within Earth's gravitational field and can
Right.
leave, like Space
And
1999.
and then our
Yeah.
tides will change at that time?
Our tides will get weaker and weaker and weaker as time goes on.
Mhm.
They were very strong when we had a 4-hour day. Okay. And then they're getting weaker. So the tides that we have now, the Bay of Fundy has like a 30-foot tide difference.
Ooh, surf's up.
Yeah, imagine what they had back when it was a 4-hour day. If
Oh
the
my
Bay of Fundy wasn't there then, though, it was a all one like Pangea kind of a thing.
Hmm.
Okay, probably at that point. But the thing is, understand that the time it takes for the moon to spiral further away from the Earth to where it's no longer part of the Earth
Mhm.
will be longer than the sun has left to live. Okay.
Funny.
And one other thing too to be interesting,
Long time.
at some point too, because the Earth is slowing down as the moon is orbiting away,
Mhm.
the moon is stealing a little bit of our momentum, so our day is slowing. So at some point,
Oh.
Earth and moon will be tidally locked, and the moon and the Earth will face each other for the rest of eternity.
Well, aren't we
Okay.
tidally locked now?
No, the moon is tidally locked to a spinning Earth, but we're slowing down. And over time, as the moon gets further away, okay, we'll slow down to a point where the moon and the Earth will be locked to each other.
Oh, I
And
see what
again,
you're saying.
that'll be a time long past the life of the sun.
Thank
It's a-
goodness.
I know it's going to take quite a
It's
while.
neat to contemplate, though, to think about.
Yeah, well, it's interesting how we've learned so much science, you know.
Mhm.
So we learned about this. Okay, here is an example. This is the penumbra of the lunar eclipse, where the moon goes behind the Earth, and here's the umbra of the lunar eclipse. So interestingly, here on January 20th of 2019, here was the observatory we were using. This is our observatory here, a SkyTour live stream. And there's yours truly sitting in my little control room. Actually, I'm sitting in the same exact place I am now.
Imagine
And
that.
this white dot appeared on the moon right here. And what that is that we are one of only 5 groups actually on the Earth that caught it. This is a meteor striking the moon at the height of the lunar eclipse.
That
That's
is
pretty
so
cool.
cool.
Yeah,
How bright it is.
it is. And it was bright for a split second.
Mm-hmm.
Now, yeah, that's because of the impact speed. It converted the energy of motion, the kinetic energy, okay,
Mm-hmm.
which is 1/2 mv squared, 1/2 of the mass times the velocity squared, okay,
Okay.
into heat, okay, of impact. And that turned this entire object molten. It's splattered out. And this object that made this bright light that you could see for 240,000 miles
Oh my
was only
gosh.
about 18 inches across.
That is so
And
cool.
from 240,000 miles away, it shows brightly, even
18
for a
inches
split
across.
second. Isn't that
Wow.
crazy?
That is crazy.
Yeah.
Well, I think we have about a minute left, Mark.
Yeah. So I wanted to share with people. This is who we are. The SkyTour live streams, a nightly foray into deep sky. You can join us. That's the old observatory, by the way, with the instrument
Beautiful.
behind me. Yeah.
Love that picture.
Yeah. And we're on Facebook, Rumble, Kick, SkyTourLive.com or SkyTourLive.org. We are a public, a 501c3 nonprofit organization.
Mhm.
Thanks to Tara. She did a lot of work for that to happen.
Thanks to him too,
Okay.
and Marianne.
Yeah. Here is the SkyTour Sonoran. That's the Arizona site. And here is the view from there. And this light is the only light pollution we have, and that's Phoenix, almost 80 miles away.
Mm-hmm.
And we have an all-sky camera. We can overlay constellations and check it out. So lots of neat things. So we have SkyTour live stream Sonoran, and then we have SkyTour Benson. Now, this is Sonoran on the left and Benson on the right, and this is Sonoran on the left and Benson on the right. This is the same object taken with the two different telescopes. So it's a wide field in the Sonoran, and then if you want to see it closer, check it out. The Benson site. And usually what we do is we open up both observatories, and we'll show a wide field view of an object and then have the close-up view of the object. And we make both of these available to all of you watching. And it's all free.
Mm-hmm.
The images we provide, the unprocessed images we give you free. And if you want the processed images, you can join our Patreon. You can do contributions at SkyTourLive.org, whatever. So anyway, thank you guys for being. Look at Toner. Thank you, brother.
Thank you, Tonala. That's awesome.
See, isn't that cool? We got so many cool people out here. Let me tell you.
Yep, great chat.
Yeah, thank you so much. And folks, thank you so much for joining us tonight. And we'll be back next week, I hope. You available next week?
Hopefully, yes. As far as I know.
Okay, I should be. I'm leaving for Denver Friday, and I'll be back Sunday. So I'm going out to teach on a Saturday, and then Sunday I'm coming back.
Oh, fine. Well,
I
great, Mark. Good luck with that.
Thank you. I won't even know I was there. It'd be so quick. Okay, and then in August I'll be out there again. We'll talk about that in another show. Anyway, thanks guys, and we'll see you on the next time, and maybe we'll stream soon.